Bueno, buenas tardes a todos. Hoy continuamos con el webinar de la Comisión de Exploración y Desarrollo del IAPG, que tiene como lema compartir experiencias y ampliar las miradas. Les recordamos que los webinars son multidisciplinarios y serán casi todos los jueves de este año a las 16 horas y se componen de 6 ciclos. Últimos descubrimientos exploratorios de la Argentina, magmatismo y sistemas petroleros, exploración offshore, microsísmica, exploración de reservorios shale de la Argentina y campos maduros. La idea de los webinars es crear un canal que permita la difusión y el intercambio de los conocimientos con un enfoque multidisciplinario y que se constituya como un medio de comunicación entre colegas de las diferentes disciplinas de las geociencias y también para todos aquellos profesionales afines a la industria. Hoy vamos a continuar con el ciclo de magmatismo y sistemas petroleros, que se compone de 10 webinars para este 2021. El mismo es una de las tareas preparatorias del simposio del mismo nombre que formará parte del próximo Congreso de Exploración y Desarrollo a realizarse en noviembre del año 2022 en Mendoza. Y la idea del ciclo de magmatismo es compartir con la comunidad geológica aquellas contribuciones que ya estén publicadas, que traten sobre la participación y los efectos, ya sea positivos o negativos, que el magmatismo tiene sobre los diferentes elementos y los procesos del sistema petrolero. También recordamos que en el canal de YouTube van a poder acceder a todas las charlas del ciclo que se han realizado hasta el momento. Agradecemos en principio a todos los oradores por su excelente predisposición, al IAPG que nos brinda su soporte en la organización y su plataforma para que hoy estemos aquí reunidos, y a las empresas que auspician el evento. Hoy tendremos una sola charla que va a estar a cargo de Olivier Galland, la cual se denomina Multiscale Structure Associated with Igneous Intrusion and Implication for Fluid Migration, an Integrated Field, Seismic and Modeling Study. La presentación tendrá una duración de 50 minutos y al término de esta vamos a disponer de un intervalo de tiempo para responder preguntas. Las preguntas o comentarios que vayan teniendo pueden ser formulados por escrito en el panel que tienen a la derecha, el panel que dice Pioneer, y las pueden hacer en cualquier momento durante la presentación, y también aclaro que pueden ser tanto escritas en inglés o en castellano. Bueno, ahora voy a pasar a presentar a Olivier. Olivier ha obtenido un doctorado en Ciencias de la Tierra en la Universidad de Reims y luego ha realizado una postdoc en la Universidad de Oslo, donde se desempeña actualmente como investigador permanente y jefe del Analog Laboratory de Oslo. Sus temas de investigación se centran en los procesos de emplazamiento de magma e impacto de las intrusiones ígneas en el sistema petrolero. Lidera proyectos de investigación internacional dedicados a revelar los impactos mecánicos de intrusiones ígneas en cuencas volcánicas y se encuentra dirigiendo actualmente varias tesis doctorales en la cuenca neuquina relacionadas con la misma temática. Olivier posee 20 años de experiencia en investigación multidisciplinaria, la cual consiste por un lado en trabajos de campo de la cuenca neuquina, habiendo realizado estudios en la zona de Volcán del Tromen, Volcán Chachahuén, Caracura, Sierra Azul y Valle del Río Grande, así también como en Europa en el área de Svalbard, mientras que por otro lado se ha dedicado al modelado de laboratorio y modelado numérico teórico. Olivier es autor de numerosas publicaciones en revistas internacionales y obtuvo el premio Ann Richter para jóvenes científicos destacados en el año 2011, distribuido por la Unión Europea de Geociencias. Además ha colaborado con la industria del petróleo en empresas como YPF, Roche, Chevron y Eneva, y lideró la reunión del LACI 6 realizada en Malargüe en el año 2019. Así que, Olivier, con esto muchas gracias y adelante con tu presentación.
Buenísimo. Muchas gracias por la introducción, Ezequiel. Voy a hacer la charla en inglés, porque mis documentos son en inglés. Entonces es un poco difícil de traducir durante la charla. So I apologize for that, but I can take the questions in English afterwards. Oh, in Spanish, sorry. I will share my screen. Yes, here it is. Here it is. Very good. Right. So yes, thanks a lot, Ezequiel, for the introduction. And I also would like to thank the organizers of the symposium for giving me the opportunity to present my work and hopefully to trigger very nice and constructive discussions with the audience and the community who is interested. I would like also to acknowledge the great work of the organizers of this symposium. It has been really professional, very well prepared, and it's very comfortable to actually be able to present the results in such very nice conditions. So during that talk, I will just present some data. I just need to, yes, okay. About the multi-scale structures associated with igneous intrusions and implications for fluid migrations. And for that, I will show some integrated results using fieldwork, seismic, and modeling study. Okay, doesn't work. Okay, now it works. So first of all, let's set the context. So we'll talk about during this talk about volcanic plumbing systems. And there are several elements of volcanic plumbing system which are interesting, and it's important to start defining them. So first of all, in volcanic plumbing system, we can have cross-cutting dikes, like these subvertical igneous sheets, but we can also have some thin tabular concordant sills, like these ones, and we can have a long, very large sills emplaced in sediments. You can have thick and bell-shaped laccolith, like this one where the magma accumulates at depth. And also when the magma reaches the surface, we can have volcanic vents and lava flows tapping everything at the top. And what is important, especially for all of you, is that in sedimentary basins, these elements of the volcanic plumbing systems are in place through sedimentary strata, and they can interact and have an impact on the sedimentary strata and so on the petroleum system. So what are the effects? So there are several effects. First, locally, we can have local maturation. So the heat brought by el laser no funciona. A ver. Yes. Okay. I cannot. Okay, very good. So the heat brought by the intrusion diffuses within the sedimentary rock and can transform the sedimentary rock, especially if the rock is organic rich matter, organic rich sediments. Also, around the intrusions, we can have fractures because the magma is coming into the sediments in a forceful manner. It's overpressured, and to propagate, you need to break and fracture the rocks. And so locally, you can have a lot of damage and hence fracturing. On the other hand, especially for laccolith, the laccolith corresponds to accumulation of magma. We can push up and jack up the overlying sediments and can produce dome, force faults, and which can be some traps for fluids. And at the end, the properties of the intrusions themselves, especially in terms of fracturing, etc., the intrusions can be permeability corridors or barriers, and it depends on the settings. And there are lots of questions behind that. And during that talk, I will focus mostly on the local damage and hence fracturing around intrusions, on the possibility of having structures that can be traps. And I will finish the presentation by introducing some aspect of corridors, barriers for fluids through the intrusions. But first of all, let's look at a close-up of the different effects and mechanical impact of intrusions. And we can have two main scales of intrusions of structures. The first scale is intrusion scale structures corresponding to the hole emplacement. For example, on this drawing, we can have a sill, and on top of that, the same scale as the sill, we have a fold, a force fold or a dome. And these force fold can be traps. This is the big scale. But we can also have a smaller scale structures at tip scale structures, because the tip here of the intrusion, they propagate, and by propagating into fracture the rock, and they can trigger local damage and fracturing. So to really understand the mechanical impacts of intrusions in sedimentary basins, we need to address and understand these structures at both the large scale, the intrusion scale, and the tip scale structures. So let's start with the large-scale, the intrusion-scale structures. So that's the first part of my talk. I will talk about force folds, domes, and faults. So why are we interested in that? Well, because depending on the type of intrusions we can have different types of structures. For example, we can just have bending above like a domed laccolith. So the question is that, okay, but is it just bent? Are the sediments just bent? So can it be a trap? But also, if it's really bent, so we can also have damage. So the question we can have is like, is there damage and fractures within the dome? So is there migration? And on the other hand, we can also reach a thickness of an intrusion such that it faults and breaks the overburden. So you can have faults. You can have some fractured reservoirs, but we can also have leakage. So really constraining these structures above igneous intrusions and understanding the mechanics of their formation is thus very important for constraining and predicting fluid migrations. But of course, we have some challenge to properly constrain these structures. First of all, we can do some field observations. Like, for example, this is a simple drawing of a structural dome where we have like outward dipping layers. But the problem is that when we have, for example, at the surface, a well exposed structural dome, it is often challenging to extrapolate surface observations to depth. So when we have that, we don't really know the shape, the thickness, and the extent of the intrusions. On the other hand, it is possible with seismic to observe, to image structures. But often, especially when we have a complex dome and also intrusions, it is possible that it's very difficult to constrain the structures. For example, this is a seismic profile that goes through an intrusion and a dome, and basically here we don't see anything. So on the seismic data of force fold can be incoherent, especially when the force folds are complex. So this is a real challenge to properly constrain and image the intrusions themselves and their associated domes and force folds. So for that, to show how it's possible to overcome this challenge, I will present a case study at Pampa Marija in the northern Neuquén Basin. And this is the picture of the dome that we studied there. So this project was a collaboration with Roche, and it involved Hernan de la Cal from Roche, José Mezcua, the CONICET Mendoza, and the PhD student of mine, Ole, who presented his work in March in this symposium. So the field area, it's Pampa Marija, is located in the northern Neuquén Basin, 40 kilometers south of Malargüe and 20 kilometers east of Bardablancas, in the seismic block called Agua Botada. And in this area, so this is a geological map of the area, and here we see in blue outcropping, so Mendoza group, surrounded by Upper Cretaceous Neuquén group sediments. So that clearly here we have a subcircular dome. And it is known since 37-38 that there is a thick intrusion, very thick intrusion below, because in this well drilled like more than 100 meters of andesite without reaching the bottom. But we don't know how thick this intrusion is. And also this dome has been mapped by a YPF commission in 1970. So this structure is known, but the exact details about the shape of the intrusion, the thickness, and the exact extent of the dome is not really well known. And of course, there are some problems. Forgot to mention that here, this is the outline of a 3D seismic block. So it actually overlaps on this dome. But unfortunately, it is almost impossible to see any structures. So for example, this is an east-west line, east-west profile going through the dome. So to the west of the dome, we perfectly see the gently westward dipping reflectors of the sediments. So it's very nice and simple structures. However, at the dome, we don't see anything. So we even don't see that there is actually an intrusion. So that's a problem. And also, if we look at the north-south trending profiles as well on this seismic data, again, the north, we have flat-lying reflectors. At the south, we have also like gently dipping reflectors to the south. But where we have the dome, we guess there is something, but it's really impossible to constrain the shape, and also we don't see anything, we don't see the intrusion. So with this data, we have no indication of the extent, of the thickness, and of the shape of the intrusion and of the dome. So we need to do something else to constrain it. And for that, we went to the fields and we spent several days mapping in the field. And for that, we were quite lucky because we have the relevant formations cropping out, especially we have thin sedimentary formations cropping out at the exposure level. We have the uppermost Agrio formation, the Witrin formation, the Tosca member, which is like a 10-meter thick limestone, and then we have the thin Rajoso formation and the base of the Neuquén. So stratigraphic well, it's very well exposed, and especially the stratigraphic contact. So it allows very good and precise mapping and overall lateral correlations of the geological observations, which allow us to really map in great detail the structure of the dome and of the force fault. And this is the results of the geological mapping. So it's a nice geological map. And you see here on the shadows, the topographic data. So this topographic data has been acquired during the fieldwork using drone surveys, and you will see it will be important. But what we can see, so we have different formations. Light brown, it's a Neuquén group. In yellow is the Rajoso formation. The light green is the Tosca member, so this 10-meter thick limestone. Then we have the Witrin formation in gypsum. At the really core, we have the Agrio shale. And on the map, we can see that we had indicated the bedding measurements. Well, we can see that on the western edge of the dome, we have very steeply bending beds. For example, we have like deep angles of up to 70 degrees. And what's interesting from here, we have almost like 2 degrees, 8 degrees, so almost horizontal. And suddenly we go to 50, even 70 degrees deep. So we have a sharp bend and we're very steeply dipping western edge of the dome. On the other hand, when we look at the eastern parts of the dome, we only have very gently dipping beddings like 10 degrees, 9 degrees, 15 degrees. So overall, the dome is strongly asymmetrical. Also, we observed some faults at the center. So it's sometimes we really observe them. Sometimes we have to guess them. We have sharp variations in terms of bedding. So we have some faults, and we can confidently say that these faults are not related to the regional tectonics. But unfortunately, the map only is not enough. So we can quite constrain the shape of the dome, but it is not enough to constrain the subsurface structure and overall the intrusion shape and intrusion thickness. So for that, we integrated the field observations and the subsurface data, which means the seismic and the data from one well. The challenge here is that we have some field observations, and the scale of field observations in meters, and the well data, the vertical scale, is also in meter. On the other hand, the vertical scale of seismic data is in seconds. So it's always a challenge to integrate seismic data and field observations, especially when we have only one well. So it's impossible, it's very difficult to convert the seismic data into true depth. So the way we did, we took two types of data. First of all, here it's a simple profile. So this is the topographic profile or the topographic map we calculated from the drone surveys. And it's a topographic profile that is the same latitude as the well. So on the well, we can also mark the depth or the altitude of the top Witrin formation. So we have two indications here. What we did, what Hernan de la Calle did, he converted this topography into seconds, so such that we could indicate on the seismic data with like a second vertical scale, the same topographic profile, and also on the seismic line, it is possible to see the reflectors of the top Witrin. So we have two independent information, which should be at the same position. So what we did the linear transformation, vertical transformation of the seismic data, such that we could match both the topography and the depth of the top Witrin. Of course, this is a linear transformation, so it's a crude assumption, but at least it allows to reconstruct properly the deep angle and the geometry of the western edge, so that we can extrapolate to the east the structure where we don't see anything on the seismic. And when we integrate that and we integrate the geological observation, it was possible to reconstruct these geological cross sections. So this is the west-east cross section, and this is the south-north cross sections. And what we can conclude is that the intrusion here is about 400 meters thick, so it's actually a big intrusion. The intrusion is, okay, I have a problem here. I don't see my text actually. Yeah, the intrusion is strongly asymmetrical with a sharp edge to the west and a gently dipping roof to the east. The dome here is faulted on the western edge. And basically the overall structure of the dome is what is so-called like trapdoor, which means that it was lifting up really much on the west, and it was tilting and rotating to the east. So it was possible to reconstruct this structure, but importantly, these conclusions were impossible to draw with only field mapping or seismic or well data. So we could reach this conclusion only by integrating the field observations and the subsurface data. And this is a very good take-home message. Good seismic data or good field observations are not enough, and we gain very much by integrating them. And of course, when we have that, then it's start to be possible to explore where we can have like traps or fractured reservoir, etc. So this is actually a prerequisite for a proper exploration. And again, what is important here is that depending on the shapes of the intrusions, we can have very different deformation patterns of the overburden. So for example, if we have like a domed laccolith, we can have a simple dome at the top first fault. So can it be a trap? On the other hand, where we have a very flat sill, we might have nothing above. And on the other hand, we have a very thick, what we call like punched laccolith. The laccolith can punch the overlying sediments and fold them. And so we can also have like a local fractured reservoir. But can we predict under which conditions we can have this flat sill, this dome laccolith, or this punched laccolith? From the field is quite difficult. That's why, to answer these questions, we are doing some laboratory modeling. And this is my new lab, which is like 6 months old. So it's a very nice tool, and it's very, very welcome to come and use it. So what's the principle? So we made some 3-dimensional laboratory models. And for that, we need to have a model magma and the model rock. The model magma, it's an oil, which is solid at room temperature, and it melts at 31 degrees Celsius, and we inject it at constant flow rates in the model. So the model is made of a square box filled with a model rock, and the model rock is made of granular materials like powders here. But the thing is that here we can have several types of model rocks. We can have low cohesion powders, like these loose materials, glass microspheres, and this one represent like weak rocks like shale. On the other hand, we can have high cohesion powders like silica flour, and you see here, you know, they can have like vertical walls, tensile cracks, which is not impossible with in the low cohesion material. And this material represents strong and competent rock like limestone. And importantly, we can mix these two member powders with different proportions, and we can get some mixtures with intermediate properties, such as intermediate cohesions and intermediate angular frictions. And depending on the cohesion we want to have, we can use different mixtures, fill the box with it, and prepare it. And during the preparation, we add the flexible net to simulate a strata, and we inject our model magma here through the inlets, and the injection triggers an intrusion. Then during the intrusion, because the intrusion is like forceful, it deforms the overburden, it deforms the model surface, and we can monitor during the experiments the evolution of the model surface using 4 synchronized cameras, and we can compute the topographic map and maps of horizontal displacements during the experiments every second. An important detail as well is that the oil solidifies at the end of the intrusion, at the end of the experiment. So then afterward, we can excavate it and get its 3D shape to compare and to correlate with the deformation observed at the surface. So we did many experiments, but I will show you two very characteristic one with very low cohesion host and one with very high cohesion host rock. So let's start with the high cohesion. Yes. So I will show two animations. To the left, it's actually a video of the image of the model surface. So you see a lot of black grains. So these are actually coffee grains to make a texture on the model surface. And here you will see the topographic map. So the scale here is 15 centimeters on X and Y. And the color scale here is like from 0, 1 to 2 to 3 millimeters. So it's very smooth. So let's see what we get. So we don't see much here, I have to say, but here we see a smooth and broad dome, like 15 centimeter broad dome of 3 millimeters of amplitude. At the end, we have the eruption of the oil at the edge here. So we have like 15 centimeter wide and 3 millimeter high dome, very smooth. And it's actually also, we can see that when we plot the same data, but a profile. So this is the same topographic map, and this would be the profile at this location. This is what we see. So we see that it's more like a bell-shaped dome. The vertical scale it's exaggerated here. It's very smooth, very broad, and then at the end we have eruption. And when we excavate the intrusion, we see that we have a thin saucer-shaped seal, so a thin seal. So sheets are associated with thin gentle deformation of the overburden. Then on the other hand, let's see what happens when we have a low cohesion model. Again, two videos, one of the model surface, and this is a video images, and this is a topographic map, and you see already the vertical scale is different. It's like more than 1 centimeter. And let's see what happens. So first, the experiment is much shorter. And you see here that we have a completely different deformation here. So we have like faulting, a lot of deformation, it's all broken up, and at the end we have the eruption of the oil. So we have a completely different pattern, deformation patterns. Let's see what happens also with the profile here. Again, it starts from flat, and then we have these big, sharp jumps where it's actually faulting and breaking. Nothing comparable. At the end we have the eruption. So here we see the deformation is really intense with lots of faulting, and when we excavate, we see that the intrusion is actually has a shape of a cork, so it's a very punched laccolith. So these are the first experiments able to reproduce both thin seals and punched laccolith, and also to simulate the associated deformation. So we produced a full set of experiments. I will not show you that, but what we can show, what we can explain, is that we can get these two scenarios. In one hand, we have the weak host rock, and on the other hand, we have the strong and cohesive host rock. And in both cases, we infer that we have an initial emplacement of a seal along strata. And in the low cohesion overburden, instead of spreading, the seal breaks the overburden, but because it's low cohesion, it cannot produce open fractures. And so the magma pushes the overburden up, which produces a lot of deformation and faulting, and the intrusion thickens to make a punched laccolith. On the other hand, the second scenario, for a high cohesion, the magma spreads, domes the overburden until a moment where it starts failing like this. But because the rocks are cohesive, it's possible to produce a tensile conduits along which the magma climbs upwards and produce eruption and to form a saucer-shaped intrusion. So clearly, these are the first models able to reproduce both types of deformation and to also simulate several types of intrusions. So now we're really trying to understand under which conditions we can expect this, and also if we have some intermediate regimes. And importantly, the next step would be to explore the effects of layering of strata. And you will see at the end of the talk that we are getting there at some point. Okay, so that was the first part of the talk. Let's look at the second part, where we focus on small scale structures like tip scale structures. I want to see what happens and what is the damage associated with the propagation of the intrusions. So part 2, tip scale structures, tip propagation and damage fracture. But first of all, have to set what the theory is. And now we're dealing mostly with sheet intrusions. I mean like these subvertical dikes or these subhorizontal sills that I mentioned earlier. And there is a theory, established theory, to explain their propagation. It's called linear elastic fracture mechanics. So what are the main assumptions of this theory? First of all, first assumption that the intrusions propagate by tensile failure of the host. So here, for example, we see a simple sketch where we have the magma overpressured, and then at the tip, it's propagating and it's failing by tensile fracturing. And as a consequence of that, we expect the intrusion tips to be really sharp and really pointy, like a fractures. And also the intrusions usually are treated as single cracks with a very simple leading edge and tip. And also a very important assumption is that the host dominantly forms by elastic bending. I'll actually put back the pointer, right? So we will see the thing is that with this theory, we expect almost no damage. So I would say, well, then it's actually pointless. However, we went to the field to try to test the relevance of this theory. And of course, we had some surprises. So I will show you a field case study to test this theory. And we studied this beautiful sill here, outcropping out as Las Loicas in the Neuquén Basin, close to Malaga as well. So this is a geological map of the Neuquén Basin. Here we have Malargüe, here we have Chosmalal, and Las Loicas is located here, a bit further southwest of where we are presented the Pampa Mareja Dome as well. The advantage of this place is that, first of all, we have fantastic exposure, so we can see here different intrusions. So we have exposures of the intrusion, which is andesite intrusion, but also of the host rock layering. So it's possible to really map the layers and to see how they are deformed to accommodate the emplacement of the intrusion. And what we did, because it's quite a big outcrop, and it's impossible to map everything. So we did a drone survey, and we computed the long orthorectified image of the outcrop. And you see the scale is 120 meters, so it's more than half a kilometer long outcrop. And on this orthorectified image, it was possible to map each layer of the host rock and to figure out how it was deformed and to map basically the damage and to see if the damage we map is compatible with the theory. And what's interesting already, we can see that the sill here is actually not made of one single sill, but it's made of several intrusions that we call like fingers. So we have here what we call the main sill. Then here we have a finger 1, figure 2, and figure 3. So it's not continuous at all. And also what we can see here, we can see that the layers seem to be quite continuous. And then suddenly they stop. Here they're completely wagging and sometimes duplicated. And then we find this red layer again below it. So we have a lot of things going on. And if we and also important thing is that the tips of the intrusions are not sharp and not pointy at all, very incompatible with what we expect with the linear elastic fracture mechanics theory. But let's focus here in between these two units here to see the damage. And there is quite interesting because we can see this red layer, as I call like layer D, is relatively flat there, and then suddenly, poof, it's faulted. But the fault here is not tensile, it's actually compressional, it's a reverse fault. And then we find the layer D again here, duplicated. Then we find the layer D also, but vertical, and then we find it wagging here. So it actually, we can see that on the field photograph. It's completely folded, completely squeezed, and completely shortened. So yes, lots of things here. The sill here is made of several segments, not only one. The tips of the sill are round, blunt, not at all sharp and pointy. The host rock layers display strong inelastic deformation. We can see like a lot of faulting here, detachment here. So nothing comparable with the elastic deformation we expect from the theory. And also the deformation in the host is compressional and accommodates local thickening, not at all related to tensile or extensional. So all the observations are contradictory or contradicting the assumptions of the theory. So actually we have a lot to learn about the distribution of the damage of around the intrusion. And so for that, we need to understand the emplacement mechanisms of these intrusions. So here's a simple sketch summary model. So here we have these intrusions. So the sill is not made of one continuous sheet, but of several fingers like this. And the fingers actually, the tip is not propagating in a tensile manner, but by pushing ahead of the host rock, what we call like viscous indenter. So it's shortening the rock instead of tearing it apart. And one sill can be made of several fingers, not only one sheet. And we can see that we have intense damage near the fingertips as we mapped here. And the damage is all related to compressional and shortening deformations. And again, these observations are in contradiction with the linear elastic fractal mechanics theory. So and still, this theory is the established one amongst the volcanology community. And we want to show that, well, we have to be careful because we have different modes of emplacement and we don't understand them. And if we want to predict where the damage is located, we need to actually understand the mechanics governing the emplacement of these systems. Field observations is not enough really for that. And we try to combine the field observations with laboratory models. We also show some laboratory models where we can try to see and map the deformation and damage associated with the propagation of intrusions. And in contrast to the first types of models, here we don't have a 3D model, but we have a quasi two-dimensional experiments, which is made of a Helle-Shaw cell. So a Helle-Shaw cell is basically a cell between two glass plates here with a 3 centimeter gap in between. And in between the glass plates, we have the model rock, which is like granular materials as well, the same glass bead and silica flower. And the model magma here, it's a golden syrup, so it's relatively sticky and high viscosity, 55 pascal second, which is injected at constant flow rate with a syringe pump, and we also measure the pressure. And the oil here, or the golden syrup is injected through an inlet. And when we have intrusions going into the cell, we can see through the glass plates the propagation of the intrusion and also the deformation of the host rock or the host material. And we follow the evolution of the model using side cameras to take serial photographs, and after we apply digital image correlation to quantify the displacement and the damage as induced by the propagation of the intrusion. So let's see what happens. The same, we use the same materials, so we also vary the cohesion. So we have like a low cohesion, low friction to simulate weak rocks, and we have like high cohesion, so we have low cohesion material. So to really test also the effect of the rock strength on the emplacement mechanism. So here, I will just switch the pointer. I will again show two experiments. We did many others, but the two main characteristic ones. The first one is actually in the cohesive molecular material. So here is the inlet, and we will see the intrusion propagating, and you can see the black grains within the white powder moving during the intrusion. Let's see what happens. So we see that the dike is propagating. We see that the host rock is moving, and at the end, the dike reaching the surface and pierce through. And in that case, in this cohesive molecular material, we have a straight sheet, so clearly like a dike. So here, the model host rock is actually a mixture of 50% glass beads and 50% silica flower. And in our experiment, actually is cohesive. So it's really like representing a rock with some strength. And in this case, the resulting intrusion is a straight, continuous dike. Great. So, but let's see what happens in another type of experiments where we have actually a low cohesion molecular material. Same setup, we have the inlet here, and we have also the material here with black grains so that we can see what happens. But let's look at the animation. Great. So you see a lot is going on here. And first of all, the shape of the intrusion is not really the same. It's not straight, but it's more like what we call like worm-like or finger shape. It resembles the fingers that we saw in the field in Las Loicas. So really here, the host material, it's actually it's a weak low cohesion. It's made of 90% glass beads and 10% silica flour only. So it's very low cohesion. And there the intrusion is not straight sheet, but it's more like worm-like discontinuous shape. So we can see we have a segment here, several segments which are discontinuous in this plane that connect in the third dimension, but here they're discontinuous. So very different shape, and so probably different emplacement dynamics. So how can we quantify that? Well, as I mentioned, with the black grains here, we can apply what we call digital image correlation between different time steps to calculate the displacements during the experiments. And this is what we can see. I will show you two animations here that will plot the distribution of the horizontal displacements in this plane. The red corresponds to displacement to the right, and the blue will correspond to displacement to the left. And to the left here, we have the high cohesion experiment, and here we have the low cohesion experiment. And it's a mistake. Here it's not the vertical displacement, but it's a horizontal displacement. Sorry about that. And let's see what happens in the high cohesion experiments. So we can see the dike propagate. We have a big halo of displacements to the right and to the left. And let's see what happens now in the low cohesion experiments. We also have this halo of deformation. But when we compare these two guys, here we see that we have like horizontal displacement along the whole length of the crack. On the other hand, in the low cohesion experiment, we only have horizontal displacement close to the tip of the crack. So dynamics of propagation is completely different. And also when, let's look at more in details. What about the damage, and especially the shear damage? Well, also here I compare two videos plotting the shear strain during the experiments in the high cohesion host and in the low cohesion host. And let's see what happens. So we have the dike propagating, and well, we have a lot of noise, a bit of shearing at the end, but very little. On the other hand, in the low cohesion experiment, we can see a lot of shear bands, shear damage, always nucleated at the intrusion tips. Again, when we compare in the high cohesion host, so it's very tough rock, very, very little damage. On the other hand, in the low cohesion experiments, we have a quite significant shear damage. So again, the damage, whether the intrusion propagates in a high cohesion host or in a low cohesion host, is rather different. I will not go into details, but at least with these intrusions, we can really try, with this experiment, we can really look at the details of where the damage is distributed. But I will show you more spectacular experiments right after. So here, high cohesion, little shear damage, low cohesion, significantly more shear damage. So if we just give a summary and conclusions of that two-dimensional experiments, in the high cohesion experiments, the dike propagates mostly, or first we have a sheet, a dike, and which propagates mostly by opening of the host rock along the entire length. In the low cohesion rock, we have a dominant shearing here at the tip with some opening at the tip. The emplacement mechanisms are drastically different, and also I mentioned that we measure the pressure, evolution of the pressure, and the pressure evolutions of these two mechanisms are completely different. So really, it's a really different emplacement mechanisms. And in the low cohesion experiment, we have fingers, which form preferably in low cohesion rocks, and on the other hand, in the high cohesion, we have like more like sheets, like dikes. And as similarly in good agreement with what we saw in the field, the fingers in the low cohesion experiment trigger significant damage in the host rock. But now I don't want to spend too much time because I want to show something which can be more relevant for the community. Especially, we have brand new experiment that we produced like a few months ago, where we try to test the effect of layers on the propagation of the intrusions, and also on the distribution of the damage. And for that, I will show 3 different experiments made by a Chinese colleague who came and visited us for a year, Xia Wen, and we're preparing a manuscript on that. So for each experiment, I will run the videos where first you will have the evolution of the intrusion with an overlay the distribution of the shear strain. And also you can see the evolution of the pressure during the experiment. So we first run the experiment, and then after explain what run first the movie, and then explain what happened. So let's look at the first animation here. And you can see really the distribution of the damage. Oh yeah, sorry, I forgot to mention, this is a homogeneous experiment, so more like the reference experiment. Right. So let's run it again, but with some explanation. So here, yes. So what we have here at the beginning, we have the propagation of a sheet like this, and with some pressure evolution. And then later on, yep, we can see here that the sheet like triggered like failure of the overburden. Yes, and then once the overburden has failed, we have a strong pressure drop in the liquids, and also the liquid follows the damage zone. So what's interesting here is that while it propagates, the intrusion triggers some damage, and once it has produced significant damage, it, as a positive feedback, it will control the subsequent propagation of the liquid. Then we can see at the very end. But overall, what is interesting here is that in these homogeneous experiments, the damage is quite simple because it's distributed more or less like, you know, close to the tip of the intrusion. So let's see what happens now when we have a layer. So what I forgot to mention is that the overall material is quite high cohesion. But now let's see what happens when we introduce a low cohesion and a low friction layer in the middle of the model. So again, I will play the video, and after we will look at the explanation of the video. Nice. So let's play it again and let's get a bit of explanation. So first of all, we can see here, so we can stop. At the beginning, we have the propagation, initial propagation of a sheet below the layer. But then at some point, what you will see that when the layer when the intrusion reaches the layer, click here, then the propagation stops. It doesn't propagate, but it halts below the layer, and where we can see that the sheet here thickens and the tip gets rounded. So when the intrusion reaches the layer of low cohesion and low friction, we have a change in terms of emplacement mechanisms, and also we have different pressure evolution. And after that, right, we have, so the intrusion has pushed here at the low cohesion layer. It failed the overburden and produced like large scale shear damage. And then along this large scale shear damage zone, the liquid follows these damage zones at the same time as the pressure drops. So here, what we can see that as soon as we introduce one layer, then we have a slightly different damage distribution, because we have, of course, like damage zones here, but the damage zones here are nucleating where we have the layer. So the layer imposes the location and distribution of the damage. And this is only with only one layer. So what happens now when we have, because in reality, in nature, we have many layers. So let's see what happens when we have actually two layers, just to see the difference. So again, the same type of videos. And here, instead of one low cohesion, low friction layer, we have two. So let's see what happens again when we have two layers. Oops. Then we'll give the explanation afterwards as well. You see, it's very rich experiment, and then we have very strong differences. So yes, so what do we get? Well, let's look again. So again, the same way, at the beginning, we have the initial propagation of a sheet, and actually it's quite several sheets, but it's propagating upwards with the same pressure evolution as usual. But then after some points, the sheet, initial sheet, reaches the first low cohesion layer, and it halts again, it stops below the layer, and the intrusion, the dike gets thicker, and also the tip gets rounded. So we get, again, we shift the emplacement and the propagation mechanism. But then later on, the liquid crosses through the first layer and then reaches the second layer. And this is where it starts to be interesting here, because when the intrusion reaches the second layer, it produces a very strong and significant shear damage, which is along the layer. And again, here the sheet halts at the upper layer. So here we have a strong evidence that the layering controls the damage distribution and also the propagation of the intrusion, because you will see that afterwards the intrusion will turn into a small seal and then propagate there. So what's interesting here, we don't have the same simple damage distribution as the first experiment, even the same as the second experiment. And clearly what we see is that the damage and the intrusion are really greatly controlled by the presence of the layering. And here we only have 2 layers of, so already it's still like a simple model. We only have 2 layers with different properties, but already it completely modifies the propagation of the intrusion and the distribution of the shear damage. And you can see really also how low strength, low cohesion layer can localize the damage. So to conclude and to summarize these experiments, first of all, I mean, what's important is laboratory models are really highly valuable tools for mapping the damage around the intrusion and understanding the distribution of damage around the propagating intrusions. These simple experiments also show that the layering deeply affects magma propagation, but it also deeply controls the distribution of the damage. And of course, these two are linked because the damage controls also the propagation of the intrusion. And these are few experiments, but these are very promising preliminary results. But ambitious future work is needed because we can try now to test the effect of many different layers of different thicknesses and of different cohesions, because we can tune and change the cohesion of these materials. I will go back to pointer and go to the next and to the last part of this talk, because now what I've showed is most only because we're talking about magmatic intrusions, but we have only looked at what happens around. What happens within the intrusions? What about the intrusion itself? So we know that within the intrusions, there are lots of things going on. And overall, there are lots of thermal assisted fracturing. And this is what has been presented during the last symposium, or in March symposium by Ole Rabel and Octavio Palma. And this is a synthetic summary figure that shows all this thermally assisted fracturing within intrusions. So first of all, when the intrusion, the seals cool down, we can have columnar jointing due to cooling. But also because we can have like hydrothermal fluids or fast maturation of the organic rich host rock, we can have strong fluid over pressures in the host rock and up to bitumen dikes. So we can have local intense maturation and concentration of bitumen that produce dikes, etc. But these are only thermally assisted and not mechanically assisted. So what about other types of fractures? And I want to show you a spectacular case study that highlights that in other types of fractures, mechanical fractures, mechanically assisted fractures can also be very important for the migration of hydrocarbons. And the case study I'm looking at now is the Cerro Alquitrán, located also the northern Neuquén Basin here. So now this time we're north of Marargüe. And this is a big collaborative project with several people. And I really want to also analyze the analysis of Héctor Villa from Geolab Sur, but many other colleagues, José Mezcua, Conicet, and Adrián Medialdea also from YPF, which really brings a lot of insights, and many others. And it's a very great project, and you will see why it's actually quite spectacular. So this satellite image of the area, and Cerro Alquitrán is here, so it's 500-meter diameter intrusion. And we can see that there is a well here, and this is located quite close to the Loma La Mina oil fields. right? And you can see already these big black stains around. And if we take a drone photograph of this black stain, so looking to the west, this is what we get. So we have a hill, which is the andesite body of Cerro Alquitrán, and then you have this big brown dark field, which are actually oil flow fields where we have active seep in this area. And you see the scale, this is the pickup truck. So that's pretty decent oil seep and bitumen seep on the edge of the andesite body. And if you look a bit in detail, so this is detailed auto-rectified image computed from drone footage, drone survey, and we can see that we mapped and found many active seeps, a big one to the north, big one to the east, smaller one to the southwest, and also we found several here in the southeast valleys. There were big active seeps, but not active anymore and produced there, and also very few small seeps within the igneous body. So the line here outline more or less the contact of the andesite body. But you can see you can have like tar pits, and we can also have like very impressive ropey bitumen flows. So if you show that to volcanology, it will say that it's a basaltic oil lava flow like in Hawaii. It's very spectacular. So, but what's interesting is that the main seeps are located close to the border and to the edge of the intrusion. So there is a clear structural and genetic relationship between the intrusion here and the petroleum seep. The problem is that we don't really know well the shape of the intrusions, and we don't know, well, we actually have no idea about the structures also in the host rock. But what is interesting here is that at the southeast, there are a few gullies, and there the oil is seeping out directly from the andesite. So there we can understand really what happens and how the andesite can control the flow of the migration of the hydrocarbons. And these are the field observations we observed there. So here there was more or less the contact of the intrusion that we couldn't see. But there what we can see is that we have these plains here, which contain a lot of fractures, and the fractures are perpendicular to this plane. So we call these plains like fracture bands. And locally here, we can have so much fractures that the andesite is brecciated. So it's a detailed field photograph. It's breccia, andesite breccia, which with some kinematic indicators indicating that the central part was moving upward with respect to the outer part, so compatible with the extrusion of the igneous body. On the map view, we can show that roughly these fracture bands are concentric, so they're related to the emplacement of the igneous body, but not with tectonics. And what we can see also in these gullies in this southeast is that here in black, this is bitumen flowing out and seeping out, and here as well. So the bitumen seeps out from the breccia and the fracture bands. And when we look at in details of these fracture bands and this breccia, there are thin emplacement brittle deformation, which means that the magma is so viscous close to the contact of the intrusion, and you have so much shearing within the magma that the magma cannot flow in a ductile manner anymore, but it breaks. So this is like breccia produced during the emplacement. And if we can, so we produce this summary figure, and we guess that this is what happens. So we have the intrusion here, punching the sedimentary host rock. And along the margin here, we have so much shearing that it produces like fracture bands, a lot of fracturing, but also brecciation of the andesite itself. We might have also brecciation of the host rock, but we didn't see that. But overall, the andesite itself is totally brecciated. So it's a magmatic brittle deformation. So this example of Cerro Alquitrán really shows and spectacularly shows that the magmatic structures within the intrusion can deeply modify the permeability structures in the area. So to really constrain fluid flow in the basins, this example shows that basin models really need to account for igneous intrusions and their properties for predicting and calculating fluid migrations within sedimentary basins. And I will end the talk with a sort of sort of summary figure that summarizes. This is a manuscript in preparations. This figure has been drawn by Dougal Jerram. We still need to edit it, but I think it illustrates very well what we mean. What we mean is that volcanism have two phases of impacts on sedimentary basins. We've had the syn volcanism phase, where basically is overall a thermal activation of the petroleum system, where we have silts, intrusions, and they heat up the sediments, they enhance maturation, and they can also produce so high fluid over pressure due to the heat that it produces hydrothermal venting, etc. So this is the syn volcanic. And then after that, we have the post-volcanic phase, where basically all the fractures and the structures related to the intrusions can be like damage around the intrusions. It can be fractures within the intrusions due to cooling or due to, for example, brittle deformation, like I showed at Seral Kitan. All these fractures can have a long-term legacy, a long-term effect on the fluid migrations, several millions or several tens of million years after their emplacement. So to fully understand really the impact of volcanism on sedimentary basins and petroleum system, we need to understand the effect of these two phases during the emplacement and long time after the emplacement. So to summarize, a lot of all the material actually presented. So the main point is that igneous intrusions are associated with structures at different scales within and also outside the igneous body. During the talk, I mostly focused outside, but as I showed, and I also as Ole Rabel showed a month ago, inside the body as well, we have a lot of structures. These structures potentially have immense impacts on free migration and trapping. And constraining these structures requires deep understanding of magma placement mechanics. And I write beyond state of the art because you saw at the last Lewicas in the seal, all the field observations contradict the state of the art established theory. So we need really to bring new knowledge, new understanding on magma placement to better constrain and predict where the damage and these fractures can be distributed. I also hope that I convinced you that laboratory modeling is a very useful tool to model magma placements and their associated structures. And now I have a brand new lab, and I'm really open to collaborations because I'm sure we can really do a very good job and can be very useful for all of you. But also, I showed at the end that the syn emplacements, brittle fracturing within the intrusions, can play a major role in fluid migrations, and to sum up as well, that not only during the emplacements by the heat, but long time after the emplacements. So igneous intrusions have long-term legacy on the petroleum systems because they completely modify the permeability distribution and so the fluid flow and the fluid migration patterns through the basins. Thank you very much, and I hope you enjoyed and you learned a lot. And I'm really open and I'm really keen now to answer your questions. Thank you very much.
Muchas gracias, Olivier. Bueno, les recordamos que pueden hacer las preguntas por el panel de preguntas y respuestas que está a la derecha. Y dado que, bueno, tenemos un tiempo limitado para las respuestas, en caso de que Olivier no llegue a responder todas, las puede responder después de forma escrita. Olivier, yendo a la primera pregunta la hace Figueredo y dice, how are these observations dependent on the viscosity of the andesitic intrusion? Should we expect different geometries for basaltic silts or lacolites?
Voy a probar a tentar en castellano y sí estoy totalmente mezclado, sigo en inglés. Bueno, es una pregunta muy relevante porque en hecho, por supuesto, estos sistemas no son solamente con respecto a la propiedad del roca-caja, pero también es como un sistema mecánico como mezclado entre un flujo de un magma viscoso y también una deformación de la roca caja. Y es una interacción mecánica entre los dos. Pero seguro que si tienen como una ondecita muy viscosa o un basalto de muy baja viscosidad, la roca caja va a ser deformar de manera diferente. Y es también lo que hacemos, lo que intentamos de hacer en los modelados de laboratorio, y también de estudiar el efecto de la viscosidad sobre el mecanismo de emplazamiento. Pero lo que se puede notar, por ejemplo, a la cuenca neuquina, y sí hay como intrusivos de composición andesítica emplazados dentro de arenisca o dentro de pelitas. Bueno, la forma de la intrusión y el patrón de deformación alrededor es muy distinto. Entonces, estoy totalmente de acuerdo que la viscosidad del magma tiene un impacto importante, pero también no debemos olvidar el comportamiento de la roca caja. Es muy importante también.
Perfecto. Bueno, la siguiente pregunta la hace Enrique Feinstein. Bueno, dice muy buena presentación y que quería saber si lograron determinar una relación entre la zona fracturada y la intrusión.
Pardon, Ezekiel. Hernan said that it's maybe better that I just take the answers in English. So can you repeat the question, please?
Yes, the question came up during the analog case where when you show the shear stress associated with intrusion, he wants to know if you get the relation between the fracture area and the size of the intrusion.
Well, that's actually a very good point, and we have not quantified that, but this is definitely what we want to quantify. And now we start having the tools for that, is to try to start correlating, I mean, from the experiments. So this is really the step we want to go further, is to really quantify the extent of the shear damage and to correlate it with the size of the intrusion. Qualitatively, there is a correlation, but we have not quantified this yet. So I mean, these are super interesting questions, and that really shows that there is still a lot to be done in great details with these experiments, but also with field observations. But that's a really relevant and very important question. I very agree, and this is basically the goal of the whole this study.
Bien. The next one is from Dennis Marshall. He wants to know, in the analog experiment you show for the dome generation in the part 1, the condition at the limit of the model are static. So he wants to know if you made the same experiment with imposed tectonic regimes such as compression, extension, or more complex strike slip, and it may modify significantly the geometry of the dome.
So I have done, actually, I started my analog modeling career with that, because the goal was to study actually the interaction between intrusions or magmatism and compressional tectonics. And so in these experiments, on purpose, so the experiments I showed, on purpose, I didn't want to introduce active tectonics because it was already complex enough. And if we want to model everything at the same time, then we would actually not understand the effect of each parameter. But in the experiments I did back in time during my PhD, yes, clearly active tectonics was affecting both the shape of the intrusions and of the dome. And especially when you have a compression, then the intrusions were really elliptical, and the domes as well were also elliptical. I observed that again qualitatively, but I didn't quantify that. But clearly, well, it's actually not so sure. You know what? Because, I mean, in the models I made like back in time, the time scale of emplacement was the same as the time scale of tectonism, which works when we consider the building of a whole volcano, of a whole volcanic system. But when you compare, for example, when we compare from the time scale of emplacement of a single laccolith, which is a few weeks, a few months, or a few years, to the time scale of tectonics, the emplacement of one single intrusion is much, much, much faster. So the tectonic strain doesn't really affect the emplacements and the shaping of everything. And maybe at the beginning, when the area is poorly deformed and subject to stress, definitely at the beginning, when the magma comes into a stressed crust, there would be an effect. But as I showed in the experiment, as soon as an intrusion starts emplacing, it totally modifies the stress field around and the strain field around, and it actually overcomes the tectonic stresses. So really, but the key thing really indeed is to decipher between the contribution of the tectonics versus local stress and strains. But coming back to the question, the existence of pre-existing faults, yes, do matter. And I am actually started a laboratory project with a bachelor student here, and we want to investigate the effect of pre-existing faults on magma emplacement. A Straxley fault, actually. But what is interesting is that depending on the viscosity of the intrusion and depending on the cohesion of the crust, we have a completely different answer. When we have a high cohesion crust with a Straxley fault, the Straxley fault has a very strong control on the magma emplacements. On the other hand, if we have the same Straxley fault but in a very low cohesion crust, then there is very little effect of the faulting on the magma emplacement. These experiments are without layering, so it's difficult to actually model a seal, but clearly in the future we want to see what happens when we both have layering and existence of pre-existing faults.
Okay, next one is from Olivier. He asked, what does the inelastic deformation around seal tips mean for fluid migration in igneous petroleum system?
Inelastic deformation for fluid migration in igneous petroleum. What does the inelastic deformation around? Well, it means that if you have like inelastic deformation, you have damage, which means that you have breaking of the rock, which means that locally it can, so maybe it was not clear, but locally, if you have fractures, then it increases the permeability or the porosity, and overall it increases the permeability. So understanding how far this damage is extending beyond the tips of the intrusion, the density of damage induced by the propagation of the intrusion, or also, I mean, if there is damage, because according to the theory of linear elastic fractal mechanics, there is very little damage. We actually observe in the field that there is damage. So yes, understanding, constraining the distribution and extent of this inelastic damage around intrusion tips is quite important to constrain the permeability architecture within the rocks at the vicinity of the intrusions.
Okay. Well, José María González congratulates you about the presentation.
Thank you very much.
Douglas Sharam asked, how far do you think that the migration fluid can be constrained within a basin? Is there a significant lateral flow, for example?
Yes, this is what I didn't mention, for example, for the Cerro Alquitrán case. So when we discussed with Hector Villar, so about the source of this petroleum in Cerro Alquitrán, so the organic chemistry suggests that the maturation of the oil seeping out at Cerro Alquitrán is not local. So the kitchen might be further west in the Cordillera, it was like deeply. So where there is much more organic matter in the source rock, and also more burial, and so more maturation there, which involves lateral migrations of 10, 20, 30 kilometers eastwards, and then the oil seeps out the Cerro And interestingly, in this area, the Vaca Muerta formations and the Agrio formations are intruded more or less all over the place with lots of sills. So we actually suspect that the migrations of these oil from the kitchen to the oil fields could be controlled by the presence of these intrusions within the source rock. It's an hypothesis, but I mean we have clear evidence that the intrusions really control at least parts of the migration. That's doubtful when you look at the field. What happens at depth is something else, but that clearly can have a strong impact whether you have intrusions or whether you have no intrusion. And you have to bear in mind as well, and this is what Ole and Octavio showed a month ago. I mean, the seals are actually fractured reservoirs, so they have some permeability and they contain some oil. So if they can contain some oil, why wouldn't they help the oil to migrate? I mean, so yes, I would answer that as long as you have intrusions and if the intrusions are partly connected over like several kilometers or several tens of kilometers, I suspect that the intrusions can really influence the lateral migrations.
Okay, we have three questions from Esteban Alfaro. The first is, what is the lithology in the seal in Mendoza?
So yeah, in Mendoza, so in Las Loicas, the seal is of andesitic composition. There's mostly andesitic. Relatively, I would say, like we don't have the viscosity or the composition because well, we didn't really analyze the sample, but it's intermediate composition. It's a bit less felsic than the Cerro-Alquitrán andesites, and it's more felsic than the basalts are erupting, for example, at the Pajunia. So intermediate composition.
The second one is if you have some reference of detected seals in conventional seismic data.
Well, usually seals are actually well imaged in seismic data. Of course, for example, Ole would argue maybe the opposite, but there are some examples where yes, we have beautiful seals detected on conventional seismic data. In details, it's more complicated because sometimes the seals are relatively thin and they can be several, so there can be some interference between the seal like complexes and the seismic wave, so sometimes it can be difficult, but overall, yes, the seals can be detected. When it comes to laccolith, and especially thick laccolith and complex deformation in the overburden, then it starts to be more complicated. And there we start having problems to detect them. So, for example, the studies of Del Pino et al. In southern Pajunia, so in this paper published in the Conexplo 2014, yeah, it shows that the seismic data is, well, there is something, we see that there is something on the seismic data, but to really say, where is it, how thick the intrusions are, and where exactly is the damage is very, very complicated. So only the wells are allowed really to really map the thickness, for example, of these intrusions.
The third one is if there are some petroleum field associated with seals or dikes reservoirs.
The answer is definitely yes. So all the oil fields in the Rio Grande Valley, so south of Malargüe and south of Pampa Amarilla, there the oil fields are within the seals. So I guess like Octavio, Ole, and also Juan Spacapan in YPF can talk much more about that than me. But yes, definitely, these can also be really important targets for exploring and reservoirs.
Okay, and the last one I have so far is from Patricio Marshall. He says that he understands that the question was already answered, so he would you say that the main factor related with the viscosity of the intrusion will be the contrast between host cohesion and fluid viscosity? Any general conclusion on that?
Yes, this is exactly that. So I'm happy because that means that what I said actually comprehensible, it's understandable, but that's exactly that. So these intrusions shouldn't be looked at the magma on one side and the host rock on the other side. It's actually a coupled mechanical system, and the intrusion of the magma is controlled both by the ability of the magma to flow, which is related to the viscosity, and the ability of the host rock to deform, which is related to elastic properties, but also cohesions and friction. And this is these two parameters and how they balance each other that will control everything. So to be a bit more detailed, it is not really the viscosity itself that matters of the magma, but this is the viscous stresses, which is the product between the viscosity and the flow rate of the magma. So we can have like very high viscosity of the magma, but if the flow rate is very, very, very low, you will have low viscous stresses. So in a way, the systems is controlled by the viscous stresses within the magma and the host rock strength and how they balance each other. And any general conclusion? So we have actually a paper in 2014 suggesting that yes, we can define a dimensionless ratio between the viscous stresses and the cohesion. And definitely there is a threshold where the viscous stresses dominate and so enhance a lot of faulting and shearing in the host rock and producing more like some types of intrusions. But when we have, for example, a low viscosity magma and place into a tough host rock, then we actually get closer to the established theory where the intrusion propagates in a tensile manner with a low viscosity magma and tearing apart and having more like very little damage. But again, I mean, volcanology, it seems like a very old science and discipline, but volcanologists have focused on the igneous rocks, on looking at the textures, the composition of the rocks. But the study of the coupling, and especially the mechanical coupling between the magma and the host rock, is relatively recent. And this is really still a complex mechanical systems. So we basically almost have everything to reveal and to understand. So it's very fascinating, and especially when we see the applications and the implications for example, petroleum industry, but also geothermal exploration. But really, we have to have a lot to understand. So any general conclusion on that? Qualitatively, yes. And now we really want to move to the quantitative conclusions. Merci, Denis.
Okay.
Pour,
So the next one is from Ricardo Manoli. He says that not far away from Pampa Amarilla, there is an intrusion drilled by a well. The intrusion is a combination of neck dike and horizontal seal. However, the well column was not an andesite seal and was not a host sedimentary rock. The column was a metamorphic metasomatic rock, which is the predictable geometric in this case.
Yeah, well, I mean, if the well, that's I mean, I don't know the case, but if the well more overall like is drilled through the metamorphic aureole of the intrusion, it sort of makes sense that we have this metamorphic metasomatic rocks. But if overall I mean, I would say, I mean, I don't know the case exactly, and I don't know where it is, so it's quite difficult to answer the question. But if the overall rocks drilled are actually these metamorphic and metasomatic rock. I would suspect that most overall the intrusion is relatively thick or steeply dipping neck. Otherwise, if it were a seal, for example, we have like the igneous rock. Just above and below that, we would have these metasomatic and the metamorphic rocks, and then above and below that, we would have like intact rocks, which is basically the metamorphic aureole of the intrusion. But if it's much more than this, then I would suspect that it's quite a big, close to the core and the center of an old volcanic system, with probably a lot of dikes and a lot of heat brought to the rock with a lot of fluids. Because also, like east of Pampa Amarilla and north of Pampa Amarilla, you have also this big intrusive complex where it's not like one single intrusion, but it's a whole volcano that was living there. So lots of dikes, lots of seals, and lots of heat brought from depth. So definitely this has the potential to completely metamorphose and metasomatize the sedimentary rocks. But then we go beyond the emplacement of a single intrusion, and we need to look at the effect of a whole volcano at that scale. And that's a bit of a different story.
Okay, I have one, Olivier. In the case of Pampa Amarilla, you have shown some dikes associated with the laccolite.
Yes.
What got my attention is that the dikes are kind of parallel instead of being radial.
Yes.
So the question is if they are using some pre-existing faults, or which is the explanation for that?
Well, there is a, yeah, I didn't really show the map of the whole area, because the laccolith, the Pampa Amarilla, is located to the west of a big volcano. I actually don't remember the name of it. I will just remember. Oops. Yeah, okay, never mind. Can you, maybe I can share my screen to show. I think it would be easier to explain. Let's see here. Yes. Can I share my screen, or no? I cannot. Okay. But yeah, so there is Cerro Mirano to the east and Cerro Tronquimalal to the north. And there actually it's an exhumed, oh yeah, I can actually share it. Yes. Right. So you see here, but so here is Pampa Amarilla, and here to the east we have the big complex Cerro Mirano, and to the north we have Cerro Tronquimalal, and these are ancient and all like whole like complete volcanoes eroded. So we will probably have a central conduits with radial dikes everywhere here, and also the same as Cerro Tronquimalal. But what is interesting, and when we look at the detail, yes, so actually we can see here this east-west trending dikes, because we were located like straight to the west of Cerro Mirano. But what is interesting is when we can reconstruct that actually the intrusion here, I should have shown that, but is overall elongated east-west. So it's more like an ellipse rather than a disk. And this is the same, the long axis of the ellipse is actually parallel to this dike. So our interpretation is that the laccolith there was fed from below by a dike with a similar trend as these dikes, which came probably after because they cross-cut the dome. So the laccolith here is like one element, we think, of the largest scale plumbing system of this old Cerro Mirano intrusive complex.
Bien, gracias. Bueno, esa es la última pregunta que veo en el chat. Si no hay más preguntas, podemos cerrar el evento. Bueno, vamos terminando la sesión entonces. Nuevamente, Olivier, te agradecemos por el tiempo y la excelente presentación. Y también al resto de los asistentes que se unieron al evento y participaron con preguntas. Antes de cerrar, comentamos que la próxima sesión de este ciclo de conferencias 2021 va a ser el jueves que viene, el jueves 29 de abril, del ciclo Últimos Descubrimientos Exploratorios de la Argentina, que tratará sobre los temas Agrio-Pilmatué, descubrimientos someros de gas en reservorio Tight, bloque del Mangrullo, Cuenca Neuquina, a cargo de Carlos Echeverría de Pampa Energía, y historia reciente de la exploración en el bloque Chachahuén, Cuenca Neuquina, a cargo de Rodolfo Guerrero y Leonardo Rodríguez Arias de IPF. Y por último, el próximo webinar del ciclo de magmatismo va a ser el jueves 20 de mayo y tratará sobre el tema Cuenca Cretácica del norte argentino y sus reservorios volcánicos asociados, el caso de Palmar Largo, a cargo de Gustavo Bergani de la UNLP y de Iván Petrinovic del CICTerra. Así que bueno, con esto terminamos el webinar de hoy y gracias de vuelta, Oliver.
Muchas gracias, Ezequiel, y muchas a todos y muchas gracias por las preguntas muy interesantes, muy relevantes.
Gracias. Chau, chau.
Chao.